Good afternoon, and welcome to the final talk of this fast and furious session. It's of course an honor to be here, so for that I must thank the organizing committee for choosing our abstract and giving me the opportunity to present in this unique format. I have nothing to disclose. So as a researcher, I often feel like much of the work we do is, in a way, storytelling. And perhaps it's because I spend a lot of time writing, either summarizing our latest story and preparing it for publication in the different journals so that we can share it with the world, or similarly, writing to the different funding agencies and, in a way, trying to sell our story so that we can get additional money to continue to do the work. But I also like to think of it in the broader sense of things, the grander scheme, if you will. And by that I mean, I like to think that much of the work we do, the culmination of the work that we do together, will eventually form the story in the next pages in this so-called book of the natural world of the biological sciences. And this, of course, is building on all the chapters that came before us, that was done by all the researchers over the years and the decades, and sometimes centuries. And I always find inspiration in this. Now, today I want to share with you my most recent story that I've been putting together, and it's about a novel gene called SLC44A2 and how we came to believe that it contributed to venous thrombosis. Now, my story begins at a part that I think many of you already know, and that is that venous thrombosis is a disease in which genetics plays a major underlying role. We know that it's heritable. Surprisingly, though, many of the genetic determinants that have been identified so far, they only really explain a small proportion of the observed heritability that we see in the clinic. Therefore, it seems that there are several factors, genetic factors, that have yet to be identified. With the advent of the genome-wide association studies, then came a tool that seemed perfect for such a task, scanning the entire genome, looking for small nucleotide polymorphisms, which could then identify novel genes, novel pathways, and novel mechanisms which contribute to venous thrombosis. Although the early results from the first GWAS studies were a bit limited, and they mostly confirmed what we already knew about genetics and venous thrombosis, eventually a meta-analysis was undertaken, which combined the work of 12 genome-wide association studies, and through this, they identified 2 novel genes, one of which was SLC44A2. Now, to most of you sitting in the crowd right now, SLC44A2 probably doesn't mean much. And you wouldn't be alone in this, because if you were to Google SLC44A2 or type it into PubMed, you would only get about 47 publications back. And what you would find is that SLC44A2 stands for solute carrier 44, member 2, and that it's presumed to be a choline transporter. Now, this is mostly based on sequence homology, and the functional studies are still a bit limited. What you would, of course, find is also the original GWAS studies, which linked SLC44A2 to venous thrombosis. And interestingly, the following year, a completely independent GWAS study was published in which they also linked SLC44A2 to self-reported thrombotic events. And this is about the extent of what was known between SLC44A2 and venous thrombosis. Now, most of what is known about SLC44A2 is that it plays a role in transfusion-related acute lung injury, or TRALI, as well as autoimmune hearing loss. And this is because it forms an epitope that is recognized by the antibodies which drive these diseases, but not necessarily a clear link between SLC44A2 and a mechanism for thrombosis or coagulation or hemostasis. Fantastic is exactly what I thought when I found this out, because here there was this project with the chance for real discovery, to identify and describe a novel gene and somehow figure out the mechanism which contributes to venous thrombosis. What I can also tell you about SLC44A2, though, is that the risk allele that was identified in the original study is actually highly prevalent. So most of you sitting in the crowd today carry at least one copy of this risk allele, because the frequency is 0.78. So then, is it important to study SLC44A2 if the risk allele is so common and prevalent? And to this I answer yes, because although it may not be used as a diagnostic marker, it may still be pointing us in the direction of a novel pathway and a novel mechanism that contributes to venous thrombosis. But how to know for sure? Luckily for us, an SLC44A2 knockout mouse was generated in the field of autoimmune hearing loss at the University of Michigan in Ann Arbor, and we were lucky enough to receive these mice in Leiden. And so we began by first characterizing the mice from a hemostasis perspective. And I won't go into too many of those details today, because during tomorrow's poster session, Julia Tilburg is giving a presentation exactly on this. But following the characterization of the mice, we went to work and started on the challenge of how can we show if SLC44A2 really has a functional role in venous thrombosis. So where to begin? So most of you are familiar that there are several different models that can be used. Each has the pros, each has the cons. So where to start? And as I said, from the literature search, there wasn't really necessarily a clear place to start, a clear link. So what was really behind this SLC44A2 in venous thrombosis? Now, in research, sometimes I think it's best to just go back to the basics. And in the field of thrombosis, we have what's known as Varicose Triad. And within this triad, it basically describes three major tenets which drive thrombosis. And those are endothelial injury, hypercoagulability, as well as stasis of the blood flow. So this gave us an idea, a good place to start. So in our case, we began by looking at endothelial injury. And we did this by inducing a laser injury on the cremaster arterioles of the mice. And when we did this, we found that SLC44A2 knockout mice had significantly less platelet accumulation at the site of injury. This was our first real clue that SLC44A2 could have an effect on clot formation in vivo. But of course, this was an arterial model, and we really wanted to study it in a venous model. So we went to work on the next model, which was one driven by hypercoagulability. And in this model, we treat mice with an siRNA, which target hepatic expression of the anticoagulants, antithrombin, and protein C. And in this way, it causes a state of hypercoagulability in the mice, which then induces thrombus formation in the large veins of the head following 32 hours. So when we treated our mice with this, we did not see any differences with regard to the onset of thrombosis. So in this case, SLC44A2 didn't seem to have an effect on thrombosis that was induced by hypercoagulability. But we did get some clues along the way. When we evaluated the blood, we found that the knockout mice had significantly higher levels of neutrophils that coincided with a significant reduction in VWF levels. So if we see these changes, how come this is not reflected back in the onset of thrombosis? Well, we know from previous work that the induction of thrombosis in this model happens completely independently of neutrophil or VWF activity. So not the best model for this. But now we have some clues. So now we know that there seems to be a role for platelets, possibly neutrophils, and VWF. And we have yet to evaluate the effect of stasis. So we came to the conclusion that the perfect model to use next would be the stenosis model. Easy, right? Well, not exactly. For those of you who are not familiar with the stenosis model, it's actually a surgical procedure, which involves tying a suture around the inferior vena cava of the mice, and this causes a 90% reduction in blood flow. It's a very delicate procedure, and one that I was not at all familiar with. So what to do? Well, luckily, we were in contact with Pierre Morange and Grace Thomas here in Marseille, and Grace happens to be an excellent surgeon. So I packed my bags, I came with my mice, mon terrible français, and my desire to know, does SLC44A2 really contribute to venous thrombosis? And so we went to work. We performed stenosis in the mice, and we did so in a blinded fashion, so that we wouldn't know the genotype of the mice until the end of the final day. And this created quite some excitement, because every day we came closer to the chance that our hypothesis might be proven true, and that SLC44A2 really does contribute to venous thrombosis. While at the same time, the opposite could be true, and we may not see discernible effects, like we did in the hypercoagulability model, and that there was no clear link between SLC44A2 and venous thrombosis. And I must admit, there were at least a few skeptics among us. But day after day, mouse after mouse, week after week, this is what we saw. SLC44A2 knockout mice have a slightly lower incidence of thrombosis, but more importantly, the thrombi that are formed are significantly smaller, both in size and weight. So therefore, these mice have a less severe thrombosis following 48 hours of stenosis. So like any good result, it only led to more questions, and so we thought, okay, well, what can be the mechanism driving this observation? And for that, we went straight to the source, and we began to characterize the thrombi, immunostaining for different cellular markers, as well as content of proteins that you would normally find in a blood clot. And from our hypercoagulability model, we thought for sure it would be something with the neutrophils or something with the VWF. But no, there were absolutely no differences when we evaluated that. What we found was that the difference really came from the amount of platelets that were in the thrombi, as the SLC44A2 knockout mice had significantly less GP1B positive area as compared to the wild type. So again, the platelets. So from this, we then wondered, well, is this really a mirror of what is happening at the initiation step, or does it have to do with propagation? So we went back to work, we repeated the stenosis, and this time we looked at a 6-hour time point. And what we found was that there was an even lower incidence of thrombosis in the knockout mice as compared to the wild type, more remarkably so, and that the thrombi that were formed were much, much smaller, thereby showing that SLC44A2 seems to have an effect in the onset of thrombosis. Now, unfortunately, this is where the story must stop today, and I leave you with the knowledge that SLC44A2 contributes to venous thrombosis, and we believe that this is through the activity of either the platelets or the neutrophils or possibly VWF. And if you're curious to know more about how SLC44A2 affects neutrophil adhesion and the activation of VWF in vivo, then I suggest that you stop by the talk of Gaia Zerka tomorrow during the morning session at 8:30 in the VWF session. And now, today, I hope that I've convinced you that genomic studies can be an important tool for identifying novel genes related to venous thrombosis. And my second hope is that more genes like SLC44A2 can be identified and validated in vivo. I think if we do this, we can continue to find maybe some novel mechanisms and novel pathways which contribute to venous thrombosis. And in this way, possibly some novel therapeutic targets. One which can lower the risk of thrombosis without the unwanted side effect of bleeding, and this, of course, would improve the lives of our patients greatly. Of course, this is always the final goal, and of course, would be the best ending to the story of all. With that, I would like to thank all the people who contributed to this story. Like most stories, this one wasn't written alone. I'd like to thank my colleagues at the LUMC in Leiden, as well as our collaborators at the University of Michigan in Ann Arbor, as well as our collaborators here in Marseille. And of course, without the funding agencies, none of this would be possible. And finally, I would like to thank you for your attention, and I hope you enjoy the rest of your time here at the ECTH. Thank you.